Welcome to the lecture series on CFD, Part 2. This is lecture 24 on multigrid methods for the solution of the Navier-Stokes equations. After a brief introduction to multigrid methods, the full multigrid procedure for the acceleration of auto iterations in simple and alike algorithms will be described. The most important ingredients in a multigrid method are the restriction and prolongation operations. Especially the restriction process requires special attention when applying the multigrid method to auto iterations while solving the Navier-Stokes equations. Treatment of boundary conditions is another important topic because the multigrid method is sensitive to consistency of boundary treatment on all grid levels. Restriction and prolongation are explained on the example of structured two-dimensional grids, but hints to implementation on unstructured grids will also be provided. An example of prediction of natural convection flow using various versions of multigrid acceleration and 6 levels of structured, boundary-fitted, non-orthogonal grids is presented next. 3 other application examples are presented in section 12.4 of the book. Finally, an analysis of efficiency, accuracy, and dependence on under-relaxation factors for the selected test case is presented. The principles of multigrid methods were explained in slides 14 to 23 of lecture 11. Multigrid methods are widely used to solve linear equation systems, that is, for the acceleration of inner iterations. Most commercial CFD codes use algebraic multigrid methods for inner iterations. Such methods are also used when solving the pressure or pressure correction equation in some explicit solution methods which do not have an auto iteration loop shown in this flow chart. For example, the non-iterative fractional step solvers. When solving nonlinear equation systems like the Navier-Stokes equations, even a direct solution of linear equation systems would not significantly reduce the number of auto iterations, that is, updates of the coefficient matrix coefficients and source terms. However, an acceleration of auto iterations by multigrid approach is also possible, although not widespread. The full multigrid procedure will be described for structured two-dimensional non-orthogonal grids and the simple algorithm for steady-state flows. Extensions to unstructured grids will be presented in slide 14. On a structured grid, each coarse control volume is composed of 4 control volumes of the next finer grid in 2 dimensions and 8 in 3 dimensions. The solution starts at the coarsest grid level as a single grid method. After a converged solution is found on the coarsest grid, it is interpolated to the next finer grid to provide a static solution. Then a 2-grid procedure begins, and so on. This diagram shows the full multigrid procedure up to the 4th grid level used to obtain steady-state solution on a series of grids. The red squares indicate a converged solution at each grid level, while blue circles indicate intermediate solutions. We start on the coarsest grid level. Let us assume that it takes 200 auto iterations to reach a converged solution at this grid level. This solution is extrapolated to the next finer grid, level 2. Here, a 2-grid V-cycle begins. After, say, 5 auto iterations at grid level 2, we restrict the residuals and velocity to grid level 1 and perform there 8 auto iterations of the simple algorithm. The difference between the initial, that is, restricted solution from grid level 2, and the solution after 8 iterations is prolonged to grid level 2, where it is added to the latest intermediate solution. This V-cycle with 2 grids is repeated until converged solution on grid 2 is obtained. It is then extrapolated to grid level 3, where it serves as the initial solution. Now 4 auto iterations on grid level 3 are performed before restricting the residuals and the velocities to grid level 2, where 6 auto iterations are performed. The solution and the residuals are then restricted to grid level 1, where 8 auto iterations are performed before prolonging the corrections to grid level 2. The corrections are added to the prevailing solution on this level and 3 outer iterations are performed. The corrections from grid level 2 are then prolonged to grid level 3, where 3 outer iterations are performed. Because this is the current finest grid, another 4 iterations are performed before restriction to grid level 2 takes place, and so on. This recursive process can be continued to as many grid levels as desired. The optimal number of iterations performed at each grid level is problem dependent. For lead-driven cavity flows, less iterations at each level are needed. The buoyancy-driven flow, to be studied in slides 15 to 23, requires more iterations due to stronger coupling between temperature, pressure, and velocities. Let us now have a look at the restriction process for a 2-grid V cycle in more detail. After m outer iterations in the simple algorithm on the grid with spacing h, the intermediate solution satisfies the following algebraic equation. Here, rho m is the residual vector after the mth iteration. Due to the nonlinearity of the Navier-Stokes equations, both the coefficient matrix A and the source vector Q are updated after each outer iteration. The solution process is then transferred to the next coarser grid with spacing 2h. The equations solved on the coarse grid are not the same as when it was the finest grid level. They must be smoothed versions of the fine grid equations. Here tilde denotes values transferred, that is restricted from fine to coarse grid, and then frozen. Hat denotes values updated during iterations on the coarser grid level. Rho tilde 2h is the coarse grid representation of the residual on the next finer grid, rho hm. All values denoted by hat are initialized by corresponding values denoted with tilde. This ensures that when the residuals on the finer grid are 0, the coarse grid equations return a solution phi hat 2h equal phi tilde 2h, that is, 0 correction for the fine grid solution. This is also how the implementation of the multigrid method in a computer code can be tested. Set the residuals on fine grid to 0, and the next coarser grid should return 0 corrections. If this is not the case, there is a bug in the implementation. While the residual on the finer grid is not 0, all values denoted by hat will change during outer iterations on simple algorithm on the coarser grid. Because of the nonlinearity of equations, the coefficient matrix and the source term are also updated. Once the solution on the coarse grid is obtained within a certain tolerance, the correction is transferred by interpolation, that is prolonged, to the finer grid and added to the existing solution. This process is continued until the solution on fine grid is converged. Richardson extrapolation can be used to obtain an improved starting guess for the next finer grid. For structured grids, simple bilinear in 2 dimensions or trilinear in 3 dimensions interpolation is usually used to transfer variable values from fine to coarse grids and corrections from coarse to fine grids. More complex interpolation methods can be used, but in most cases the simple second-order technique is quite adequate. Only when discretization methods of higher order than second are used, interpolation techniques of a higher order should be also used for restriction and prolongation operations. Another way to transfer a variable from one grid to another is to use the gradient of that variable at the CV centers of the grid on which the variable was calculated, coarse or fine. For example, to restrict the variable phi from fine to coarse grid, the coarse grid variable value at node C can be computed as shown by this expression. We extrapolate from each fine grid node Fi to node C using variable value at the fine grid node, its gradient there, and the distance vector from node Fi to node C. We sum all estimates and divide by the number of fine grid cells in one coarse grid cell. Weighting could be also made proportional to distance or cell size. The coarse control volume does not need to know which fine control volumes belong to it. It only needs to know how many there are. On the other hand, each fine grid control volume, a child, knows to which coarse grid control volume, the parent, it belongs. This is unique because it has only one parent. The coarse grid correction is transferred to the fine grid in a similar way. We calculate the gradient of the correction at the coarse grid cell center and compute the correction at the fine grid nodes which lie within this control volume as a function of the correction at node C, its gradient there, and distance vector from node C to nodes Fi. This approach is applicable to arbitrary unstructured grids. Other kinds of polynomial extrapolation can also be used. If coarse grid control volumes are made of an integer number of fine grid control volumes, conservation properties can be used to restrict mass fluxes and residuals. Mass flux through a coarse grid control volume phase is obtained by summing mass fluxes through the corresponding fine grid phases. During outer iterations on the coarse grid, mass fluxes are corrected using velocity corrections, not recomputed using U hat. To ensure that corrected mass fluxes satisfy the continuity equation, a pressure correction equation needs to be solved as in a regular simple algorithm. If coarse grid control volumes are not made of an integer number of fine grid control volumes, initial mass fluxes must be calculated using restricted fine grid velocities and corrected to satisfy the continuity equation. The coarse grid representation of fine grid residuals is obtained by summing residuals in fine grid control volumes which make one coarse grid control volume. To compute the coarse grid representation of fine grid residuals when coarse grid control volumes are not made of an integer number of fine grid control volumes, we first compute specific residuals on the fine grid by dividing residuals with cell volume. The specific residuals are restricted to the coarse grid in the same way as other field variables, velocities and scalars. Then, the specific residual is multiplied by the coarse grid cell volume. Because pressure terms are linear, we do not need to restrict the pressure from fine to coarse grid. On the coarse grid, momentum equations only see the difference P prime equal P hat minus P tilde. The initial value is 0, not to be confused with the pressure correction from simple algorithm, which corrects this quantity in each outer iteration on the coarse grid. Multigrid methods for simple and related algorithms are not widely used. One reason is their sensitivity to the consistency of all approximations, especially boundary conditions. Here is an example from implementation of boundary conditions at symmetry planes. Boundary condition at symmetry plane for a scalar variable phi implies zero gradient in the direction normal to boundary. It is usually implemented in finite volume methods by setting the values at boundary nodes equal to the values at the centers of control volumes attached to the boundary. In this figure, this means that on the fine grid, the variable value at the boundary node FB1 is set equal to the variable value at node F3, and the variable value at the boundary node FB2 is set equal to the variable value at the cell center F4. For the coarse grid, the variable value at the node CB is set equal to the variable value at the node C. The restricted variable value at the center of the coarse grid control volume, C, is usually computed using bilinear interpolation from the centers of the four fine grid control volumes, F1, F2, F3, and F4. The restricted variable value at the coarse grid boundary node CB could be computed by linear interpolation from fine grid boundary nodes FB1 and FB2. However, this would be inconsistent with the boundary condition. Restricted value at node CB should be set equal to the restricted value at node C because this is what will be applied to phi hat during outer iterations on the coarse grid. Analogously, prolongated values at boundary nodes FB1 and FB2 should be set equal to those at nodes F3 and F4 not interpolated from boundary nodes like CB. The multigrid idea can be applied to unstructured grids, even if the coarse and fine grids are not related by systematic refinement or coarsening. The grids may be arbitrary. It is only important that the solution domain and boundary conditions be the same on all levels, and that one grid is substantially coarser than the other. Otherwise, computational efficiency is not improved. The restriction and prolongation operators are then based on generic interpolations. Another option for unstructured grids are algebraic multigrid methods. The coarse grids are not explicitly generated. One creates coarse grid equations by summing equations from a certain number of fine grid cells. The decision which fine grid cells to group together is usually made according to cell aspect ratio, joining cells with the largest common face. Let us see how the multigrid method described in preceding slides works for a laminar, buoyancy-driven flow, natural convection, in a rectangular cavity enclosing a hot cylinder. The solution domain is symmetrical, so only the left side is used with symmetry plane condition along the vertical symmetry plane. The side walls are cold, while the top and bottom walls are adiabatic, that is, perfectly insulated with zero heat loss. A hypothetic fluid with properties listed here is used. Together with temperature of cold and hot walls and cavity dimensions, the Rayleigh number of 1 million is obtained. Because the Prandtl number is set to 0.1, this means that the Grashof number is 100,000. These two plots show the coarsest and the next finer grid out of 6 grid levels. The grids would be of O type if the whole domain was used. For the half domain with symmetry boundaries, we have an H type. The lower part of symmetry plane is the west boundary. The upper part is the east boundary. The cylinder surface is the south boundary, and the bottom, side, and top walls make the north boundary. The grid generation code, the flow solver, and the code for post-processing and plotting are available in source form at the Siemens community page. See the last slide for the link. This slide shows the next 3 grids, grid 3, grid 4, and grid 5. The finest grid is not shown because it is so fine that lines could not be distinguished without a zoom in. The number of cells in each direction is doubled with each refinement. The finest grid, level 6, has 512 times 256 cells. This is very fine for a 2-dimensional grid used to compute a steady-state laminar flow. In simple geometries, one can derive a simple expression for the Nusselt number, which is the ratio of heat transfer due to convection and conduction normalized by the heat transfer by conduction alone. For this geometry and boundary conditions, such a simple formula does not exist. For this reason, pure conduction is considered first by solving only the energy equation. This would not be possible to do experimentally because as soon as temperature differences are present in fluid, it is set to motion due to resulting density differences and gravity. In a numerical simulation, there is no problem in solving the energy equation alone. The left figure shows the temperature distribution for the case of pure conduction. The plot on the right shows isotherms for the case of natural convection at the Rayleigh number of 1 million and Prandtl number equal to 0.1. A significant difference is immediately visible. The isotherms are much denser near isothermal walls, the fluid is much hotter under the top wall, and it is much colder above the bottom wall when natural convection is present. This slide shows isobars, that is, the lines of constant pressure, streamlines, and velocity vectors in the cavity. The gravity alone would lead to pressure increasing from top to bottom in the direction of gravity vector. Due to fluid motion, we see that the lowest pressure is obtained at cylinder wall, where the highest velocity is obtained. Here, the heated fluid rises upward. Near top wall, the pressure increases because the fluid stream impinges against it and needs to be redirected downward. At the bottom wall, Both gravity and fluid stream impinging onto it lead to an increase of pressure. The maximum pressure is obtained directly at the bottom wall. Note that isobars are sometimes orthogonal to walls and sometimes not. Zero gradient condition applies only to the pressure correction at boundaries where the velocity is prescribed. Here, zero velocity at a wall, no slip condition. When the converged solution is obtained, pressure correction is zero everywhere, but the gradient of pressure in the direction normal to wall boundaries may be non-zero depending on local conditions. Velocity vectors and streamlines show one large primary vortex and several secondary vortexes in corners and above the cylinder. The heated up fluid cannot follow the cylinder curvature all the way. Once the pressure along wall starts increasing, fluid separates from the wall and flows upward, leaving a recirculating vortex with hot fluid above cylinder. This slide shows convergence of iterations on grid 4, 128 by 64 control volumes. Shown are residual histories for velocity u and for temperature T. SG denotes single grid method, starting on grid 4 with an initial guess, which is zero velocities and pressure and constant temperature. PG denotes single grid computation, starting on grid 4 with initial fields obtained by interpolating the solution from grid 3. MG denotes the multigrid method, starting with an initial guess on grid 4. And finally, FMG denotes the full multigrid method, starting on grid 4 with initial fields obtained by interpolating the solution from grid 3. Full multigrid method requires only 50 iterations. Multigrid method, starting on grid 4, requires 105 iterations, while both variants of single grid method, SG and PG, require more than 3000 iterations to reduce the temperature residual norm below 10 to minus 6. This slide shows the same information as the preceding slide, but for the finest grid, 512 by 256 control volumes. Shown are residual histories for velocity u on the left and for temperature T on the right. Full multigrid method requires 36 iterations. Multigrid method starting on grid 6 requires 116 iterations, while single grid method would require tens of thousands of iterations to reduce the residual norms below 10 to minus 6. This slide shows the convergence of local heat flux distribution with grid refinement, shown here on the left, and temperature distribution on grid 6 on the right. Zero angle position is at the top of cylinder. The heat flux is lowest there because the fluid has heated up in the recirculation zone above cylinder and is not able to take the heat away. The maximum heat flux results at around 158 degrees from cylinder top, where the cold fluid accelerates after coming into contact with the hot cylinder. The curves from the two finest grids cannot be distinguished from each other in the plot, indicating the discretization errors on the finest grid are relatively low. The plot on the left shows the convergence of the total heat transferred from hot cylinder to fluid with grid refinement. A monotone convergence toward grid-independent solution is obtained. Richardson extrapolation is used to estimate the grid-independent value of the total heat flux. A normalization with the heat flux obtained with pure conduction leads to the Nusselt number of 2.908. This indicates that heat transfer is approximately 3 times more intense with natural convection than with conduction alone. By subtracting the heat flux computed on each grid level from the grid-independent value estimated using Richardson extrapolation, error estimates for each grid are obtained. The variation of discretization error with grid refinement is shown in the plot on the right. The grid spacing is normalized with the representative spacing from grid 1. We can see that by reducing the grid spacing by 1 order of magnitude, the error is reduced by almost 2 orders of magnitude, indicating a nearly second-order convergence. Let us now see how the under-relaxation factors for velocities pressure, and temperature affect the performance of full multigrid method. The first table shows the number of iterations in full multigrid method required to reduce the residual norms below 10 to minus 6 on grid levels 4, 5, and 6 for different combinations of under-relaxation factors for velocities, pressure, and temperature. The simplified pressure correction equation is solved once per outer iteration, and because of grid non-orthogonality, the under-relaxation for pressure must be kept low at 0.1 in all cases. With 0.2, iterations are diverging. We have seen in slide 25 of lecture 19 that the number of iterations required to reach the convergence criterion in a single grid method strongly depends on under-relaxation factors. The finer the grid, the stronger the dependence. This table shows that the multigrid method is not very sensitive to the variation of under-relaxation factors. The second table shows the number of iterations in full multigrid method required to reduce the residual norms below 10 to minus 6 on grid levels 4, 5, and 6 for different combinations of under-relaxation factors for velocities, pressure correction, and temperature when the pressure correction equation is solved twice, for P prime and P double prime. See slide 27 of lecture 23 and section 9.8 in the book for details. The dependence on under-relaxation factors is somewhat larger than in the first table, but still much smaller than in the single grid method. Note that the solution of the second pressure correction equation significantly reduces the number of outer iterations, practically by a factor of 2. The computing time is not that much reduced because the pressure correction equations require more inner iterations per outer iteration than momentum and energy equations. In the present example, full multigrid procedure with V cycles was used. Other types of cycling between grids are also possible, F cycle, W cycle, etc. The effects on efficiency may be significant when comparing multigrid versions among themselves, but the differences are not large compared to those between multigrid and single grid computations. As already mentioned, more iterations at each grid level are required when computing natural convection flows than when solving only the Navier-Stokes equations, approximately twice as many. Let me summarize the main takeaways from this lecture. Multigrid methods can be used to accelerate the convergence of outer iterations when computing steady-state flows using simple and related algorithms. Because of the nonlinearity of equations, we solve on coarser grids for an improved approximation of the fine grid solution rather than correction, as is done when solving linear problems. Care is needed to ensure that no correction to the fine grid solution is computed on coarser grids when the residuals on the fine grid are 0. Restriction and prolongation operators for transferring solutions between grids need to be consistent with boundary conditions. Application to a steady-state laminar natural convection flow shows that full multigrid method leads to speed up of convergence by a factor of 100 or more on fine grids. More details and examples are available in section 12.4 of the book.